Thank you. So, so as well as the University of San Francisco, I'm also the co-founder of a self-funded lab called fastai. Fast.ai actually is very related to this quote from this obscure person, a guy called Dennis Allison in 1972 created something called the People's Computer Company, where he said, computers are mostly used against people instead of for people, used to control people instead of to free them. Time to change all that. It was interesting to me reading this quote because we saw something similar happening with AI, which is that AI is this super powerful set of technologies that we saw were in the hands of a kind of an elite few. That elite few was pretty homogeneous and were not necessarily people who deeply understood what the most pressing societal problems in the world really are, or had the data to fix them, or understood the operational constraints necessary to do something about them. And so when we started looking into the question of like, well, what would it take to make AI more accessible, so it's not in the hands of this elite few, we found that the answer was quite difficult. So for example, my co-founder, Rachel Thomas, asked one of the top researchers in 2013, I think it was, at a meetup, how do you actually initialize your models in a way that they train from a good starting point? And he said, his response was, oh, that's part of a bag of tricks that nobody publishes. So it's like you couldn't even start training because you didn't even know how to start with your weights. So we kind of set out to change that. We started this self-funded lab called fastai, where we basically tried to figure out, can we get deep learning specifically into the hands of domain experts, by which I mean like radiologists or journalists or lawyers or whatever. So Fast.ai does a number of things to try and do this mission of making deep learning accessible. The main thing I'm going to focus on today is that we write software. And the software we write is basically to try and make it so that it's easier to get really good results with deep learning. We also teach, which is a lot about basically teaching how do you get really good results with deep learning, and a lot of time part of the answer is use the software we've written. Some of the time it's not. We do a lot of traditional or semi-traditional academic research. Anytime we come across something where we think, oh, this is like something that deep learning can or should be able to do really well, but currently it doesn't do well, or it's expensive, or it requires a math PhD or whatever, we do the research to figure out how to make it easier and cheaper and not need much data. And then there's kind of no point making something accessible if each person who comes into your field is now an island, with no community to reach out to and share their work and get support from and so forth. So we also have developed the world's largest deep learning community, which is just this super friendly, engaging, and also highly competent online place. Before I tell you about our software, I'll give you a quick sense of some of the stuff that kind of goes into it around the research and training that we do. Our online course, so we don't have any revenues or profits or anything. Like I said, we're a self-funded lab, so everything we do is free and open source, and there's no ads or anything like that. So we have this course online, Practical Deep Learning for Coders, which I don't know for sure, but I think it might be the most popular deep learning course in the world. There are 14 lessons, about 28 hours of material. Each lesson is, you're expected to do about 10 hours of work. So, you're ending up doing well over 100 hours of pretty intense work. Currently, it assumes that you've had at least a year of solid coding experience, which is a prerequisite we would love to get rid of. One of the interesting things was, after a course a couple of years ago, I put up a post on our community forums saying, after the first class, saying like, hey, did anybody build anything cool after today's class? And this was a while ago. There's now more than 1,000 people who answered that by saying yes, which was super cool. And so people who, as I say, they come into this with a year of coding experience, but no other prerequisites. So from all around the world, so no math prerequisites other than high school math. So one person said, oh, I'm from Trinidad and Tobago, and we have certain kinds of islanders, and I built a classifier to figure out what kind of islander a picture is of. Somebody else did zucchinis versus cucumbers. Somebody else picked aerial photos of the Earth and built something that with 85% accuracy could figure out what city a picture was of. Somebody else classified types of Panamanian bus. The interesting thing about these is batik cloth. They're generally with, here's one, 300 pictures across 50 types. So like it's quite common to have like less than 10 images per class. A lot of people getting good results with less than 50 images overall. So like definitely kind of showing you don't need, and this is after one lesson, so you don't need a PhD and a data center and a million images and so forth. So we're kind of trying to show that the baseline required to get good results from this technology are maybe not as high as people assume. This is an example of figuring out different types of condition of buildings in Tanzania. This kind of stuff's super important for like earthquake resilience and other disaster resilience. There are people working on this field very actively to help get teams to the places that really need the help after a natural disaster. Another student got straight away a state-of-the-art result, better than any academic paper for Devangari classification. One of the interesting things that happens when you bring people in from all around the world who, you know, they often tackle problems that just haven't been tackled before, whether it be, you know, Trinidad and Tobago person recognition or Devangari character recognition. Often it turns out that to kind of create the best ever result, it doesn't actually require that much because there just hasn't been that much resources thrown at it before. So that's been cool. One of the interesting things is to see how people kind of take the tools and adjust them to work in their domain. So somebody was looking at, after lesson one, was looking at environmental sound classification. And after lesson one, you only know computer vision, right? So they basically took sounds and turned them into pictures by doing spectrograms of them and threw it through the models that we taught in lesson one. And again, it turned out they got beat easily the state-of-the-art result from the academic literature for environmental sound classification. Elena Harley is amazing. She's from Human Longevity International. She's now created a whole bunch of projects showing significant advances in genomics. Again, she doesn't have a background in AI, but has a very strong background in genomics, working with Craig Venter's lab. And then there are some folks who go kind of above and beyond. So one of the things we did in lesson 7 was we showed people how you can do generative image models, which is where you take a deep learning network where the output's not a classification, but it's another image. And one of the folks in the course, Jason Antich, thought, oh, I wonder if that could add color to black and white images. And he tried it out, and it turns out the answer was, yes, you can. And he's now spent over a year working on this, and this is an example of his model that colorizes this black and white image. And as you can see, it does a beautiful job. And actually, this technology has just been acquired by, it's called MyHeritage, which is like the biggest kind of family tree thing in the world. And they now, I think in the first week, something like 1 million images from customers got colorized. So this is something that kind of started as a FastAI student project. This guy was working at an insurance company and turned into this passion project and is now a commercial thing that you can go and use. One of the nice things has been to see how groups of domain experts kind of get together and build cool stuff. So a lot of radiologists have gone through the course, and there's this kind of really strong alumni network of FastAI radiology kind of practitioners. So Alexander is one of those. He's now published a paper. He's won a Kaggle competition. I don't know how these people who are working doctors' hours are able to do this, but there are people who, it's really cool. There are now, young doctors and residents who are also world-class deep learning practitioners, and that's been great to see. This is a cool example. So one of our alumni, Christine Payne, who seems everything she does in the world, she does incredibly well. She actually went to OpenAI shortly after finishing her FastAI course and was working super hard in lots of other areas. She built a neural network music generator, which was such a big thing that the BBC Philharmonic Orchestra commissioned to actually play some of the music that this thing built. So she's now at OpenAI, which is a pretty cool research lab focusing on deep learning. And one of the interesting things about Christine is that before that, she was a pianist. So this is a good example of taking a domain expert and giving them a tool and seeing what they kind of build with it. Not just a pianist, she's done 1,000 different things, but that was one of them. As well as the courses, I mentioned we do research. One of the things I noticed early on in this research was that people in the deep learning community didn't seem to talk to each other as much as they could. So, for example, there was the NLP people and there was the computer vision people. When you build software and create courses, you kind of have to be cross-disciplinary within the groups. And I noticed all the cool stuff from computer vision wasn't being used in natural language processing, which I thought was weird. So I started asking,
That's normal.
yeah, so that's normal. So I asked my friends in NLP, how come you're not using the computer vision stuff? And the answer was always, that'd be a waste of time. NLP is special, it's unique, but I did it anyway. And literally within 4 hours of trying basic computer vision transfer learning techniques, I had broken the state of the art for one of the most important classification data sets in NLP, the IMDb data set. So that got turned into a course. Sebastian Ruder, who was then doing his PhD, saw that and said, that's amazing, you should turn it into a paper. So Sebastian and I wrote a paper together, and that became ULM-FIT, which became pretty much the first really strong example of general transfer learning in NLP. Alec Radford at OpenAI then took that and turned it into GPT, which became GPT-2, and Google took that and they turned that into BERT, and now we've got this flowering of transfer learning in NLP. So often it just requires this, small little observation, not a whole lot of time, not a whole lot of effort to say, hey, maybe these approaches would work well. So Sebastian's now at DeepMind, and a lot of people are now talking a lot about the power of fine-tuning and transfer learning in natural language processing. One of the challenges in the field of deep learning has been all the they're called hyperparameters, or the settings you have to tune to get something to train properly. So one of the things we've tried a lot with our research is to figure out how to make it so you don't have to. We did something pretty obvious, which was to look at a whole bunch of hyperparameters, and then we worked with a group called Fellowship AI, who are basically a bunch of mainly PhD graduates from non-math and machine learning fields, so kind of economics and political science and whatever, who were interested in getting into AI. And they helped run these experiments where across lots of different kinds of data sets and lots of different kinds of hyperparameters, we basically found a set of hyperparameters. So kind of yellow means it's kind of the midpoint set of curated hyperparameters. Found a set of hyperparameters where basically there was no data set and no set of other hyperparameters that was very significantly better. So you can see how this goes into the software. That kind of becomes then the defaults in the software. And then when we find places where it's like, okay, this hyperparameter does matter, and it depends on this feature of the data set or this feature of the loss function, we can put those rules, those just, simple heuristics into the software. So we kind of try to replace, Google has this AutoML thing where they run thousands of models, and it costs a fortune to figure out what the best optimal set of hyperparameters are. And we kind of try to say, okay, we don't want people to have to pay Google thousands of dollars to run every possibility. Let's just give you a set that's going to work first time. So this is kind of our approach to, one of our approaches to making things more accessible. One of the things we really struggle with is people using lots of money and lots of computers to do cool things is super popular in the mainstream media. So, and companies like Google and OpenAI want to tell this story about how they have more resources than everybody else, and they use those resources to get great results. And the problem for us is we keep meeting people who I say, hey, if you ever thought about applying deep learning to your problem or seeing if deep learning might be useful in your field, and I keep hearing the answer, I'm not going to try because I don't have Google's computers, I don't have their amount of data, I can't usefully contribute to this field. So we hear that all the time. So from time to time, we try to make our own little stamp to say, even a little 2-person self-funded research lab, with a bunch of new students can do, this kind of work. So the main one we did particularly was Dawn Bench, which was actually a competition run out of Stanford. Very cool competition where they said, hey, rather than seeing who can be the most accurate on ImageNet, which is a very popular computer vision data set, who can train it the fastest to, approximately state-of-the-art level. So kind of the first to dive in was Intel, and they published a result on the leaderboard using 1,000 computers networked together, and they got, I don't know what it was, like 9 hours or something. And then Google had a big team from Google Brain working on it, and they published something that was like, I can't remember, maybe it was like 4 hours using a whole pod of TPUs working in parallel. And then one of my students came to me and told me about this Dawn Bench thing and said, maybe we could try to give it a go and see if we can not come last, which is always a good goal. So we thought we'd see if we can not come last. And we won. We won using one computer. And the key thing we did was just the stupid stuff that nobody else had bothered to try. Most importantly, rather than training on the large ImageNet images, let's make them small and train on the small ones, right? So 64 by 64 image compared to a 300 by 300 image, you're going to do it 10 times faster, even if you only have one computer. But it's a picture of the same thing. It looks the same, it's just a bit pixelated. And it's that kind of common sense thing where you're like, okay, if a human can see that a 64 by 64 image and a 300 by 300 image look the same, a computer's, deep learning algorithm is going to see they look the same too. So we trained 95% of the epochs on these small images, and then at the end we gradually scaled them up. And the cool thing is that not only is it way faster, because you're just doing less compute, you also get a very nice natural data augmentation, which is you're actually giving the computer different resolution images during training, so it actually tends to overfit less, so you can do less epochs. And then we did other things, like we kind of try to find the research papers that don't get noticed because they don't come out of fancy universities like Stanford. So, for example, there's a guy called Leslie Smith at the Naval Research Lab, which he's basically the only guy working there on deep learning stuff. Nobody's heard of that lab really, at least for deep learning. But it turns out that he published some amazing insights, one of which he discovered that there were certain sets of parameters in certain situations where he could use a 10 times higher learning rate than previously known approaches and train things 10 times faster. And he called this thing superconvergence. Academia being what it is, he got rejected from every conference. It never got published, but thanks to the modern world, there's a preprint on archive, and we could read it, and it was clear that something weird's going on. So yeah, Leslie and I and fastai have kind of collaborated informally and figured out, with the help of lots of other people around the community, how to train neural nets super, super fast. And one of the nice things is that there's a great link to the course, which is that we tend to say like, hey, here's this paper we found by this guy called Leslie Smith, here's why it's interesting, and then suddenly we've got tens of thousands of people who are also enthused, and so it tends to kind of percolate up. So there's this nice, kind of mesh of things going on. So that's kind of that's the feed in to the software. And I'd say honestly, the focus for us is very much moving from education to software development. Because when we started, it was like, okay, let's teach what's already there. And then once we felt we were doing the best we can of that, then it's like, okay, well, let's try and make it so there are better things to teach. And so ideally, it would be nice to get to a point where deep learning was as easy to use as the internet is on an iPhone. We're a long way away from that yet, but the only way to get there is not by improving the training, but by improving the software people are using. So we have many steps to get there. But as Dennis said in the introduction, we're kind of at step 2 of the software, which is we've just spent the last 18 months trying to create the very best library for deep learning that we can. One of the, I think perhaps the most interesting insight about this development process for me is I have far more experience as a software engineer and coder than as a deep learning person. I've been coding for many decades, and I love refactoring. I think refactoring's super cool. There are very few people with really deep software engineering backgrounds in the deep learning world, and so things like refactoring don't happen very much. FastAI 2 is what happens when you bring refactoring to deep learning. And it's actually quite amazing what happens. So the first thing I'll point out is what we see here, which is that you end up with a layered, decoupled API. So people often ask us, is FastAI designed like for beginners and end users to be like a quick out-of-the-box thing, or is it designed for researchers, or what? And the nice thing is with a layered API, the answer is yes. It's all of those things, which like to a software engineer does not sound weird, but to a machine learning person, that's mind-blowing. So we have this applications layer where these 4 applications are basically things where deep learning is pretty mature, pretty effective, being used in industry and commercially right now. We've done enough research to figure out kind of how to package it in a way it's going to work for you with no more than a couple of hours of training. So that's the application layer. The mid layer is what all the applications are built on, which I'll describe shortly. But they're the things which kind of researchers and people building new applications would build on. And then the mid layer is built on this foundation layer, which has some things that are not at all new, but they're new to this world. So to give you an example, object-oriented tensors. So a tensor is kind of the basic building block of deep learning. It's just an n-dimensional array, not a jagged array. So that's the thing that kind of makes it a tensor for computer scientists. A tensor for physicists is a bit different. In TensorFlow and PyTorch and the libraries people use day to day, the types of tensor are float tensor, byte tensor. That's kind of what we mean by type, right? So when you have a tensor, there's not much you can do with it. You can't display it or pass it to, or flip it or translate it or whatever. And the rest of the world, software engineers use types to describe the semantics of what their thing is. And a tensor always has semantics. A tensor represents a 3-channel normalized mini batch of images in channel first access order, for example. So create a type system that can understand those kind of concepts. So that's what we did, right? As it's not remotely innovative, but it hasn't been done in this field before. So we now have a library where you can dot show a tensor and it works, or you can dot predict on it and it works. So that's kind of some of the foundational stuff. So the applications, so this FastAI library, as Dennis mentioned, there's a book coming out about it, which we just have to finish writing. And there's a paper which just came out about it as well.
I presume that pre-ordering it puts pressure on you? You get it out.
Yeah, we have enough pressure. In the applications layer, there's kind of some stuff that's across all the applications, like transfer learning, for example, is fundamental to FastAI. Transfer learning is a thing where you don't have to start with a neural net that can't do anything at all. You start with somebody else's neural net that does something a bit like what you want, and then you fine-tune it. That's what transfer learning is. It turns out that how you transfer learn matters a lot. Very few academics have spent any time focusing on this question. It's not a popular research question, but it's like just about the most popular, most important practical question. So we spent a lot of time figuring out how to do this well, and it's all built into the FastAI library. So for every application, you can literally call a fine-tune method, and it does all the transfer learning best practices. We also try to make it easy to figure out what's going on, and specifically if something's not going well, why isn't it going well? So we provide these kind of graphs that show what's happening. Each line is a different layer of the model, and the x-axis is different mini batches being passed through, and we look at the means and standard deviations of the layers in various different ways. One of the really interesting ones is this thing which we call the colorful dimension, which these 4 pictures are 4 layers of a neural network that's training. The x-axis is mini batches, so it's kind of time, if you like. And each set of pixels represents a log normalized histogram of all of the activations in that layer. So when you see kind of all the color down here, it indicates that nearly all of the activations are close to 0. And when you see it spread out like this, it means that there's activations throughout the neural net. And generally speaking, this is bad because it means that you've got like a very sparse set of activations, so it's not doing much computation. You've got tens of millions of activations, but most of them aren't doing anything at all. And so there's this fascinating thing when you create this picture. You discover that for many neural nets, when you start training, the kind of spread of activations goes up nicely, and then it crashes and then goes up, but it kind of goes up exponentially and crashes and goes up exponentially and crashes. So we'd never seen this picture drawn before, before we created this. And it's this sudden like aha moment where you're like, this has got to be bad, right? Because every time it comes up and crashes, it's got a whole lot of work to do to make these activations anything other than 0. And you can see that by the time you get to the 4th layer, it's very, very clear. So one of our students, actually, Stefano, spent a lot of time during a course on like drawing up different ways that we could represent this and helped us create these beautiful pictures. But it actually turns out, after all, that one line is really what you want, and that line is at each mini batch, what percentage of the activations for a layer are 0. And so for this training, in layer 4, you can see that basically you get to nearly all of them as 0. And so you would never know this without these pictures. You would just be like, oh, my model's 90% accurate. That's a bit disappointing, but so be it. But actually, if you look inside, you realize my model's not working well at all. So in this case, we realized that there was a key issue that the main activation function, called the rectified linear unit, actually doesn't have a mean of 0. ReLU basically removes all negatives and replaces them with zeros, which by definition has a positive mean. So we just subtracted 0.4 from ReLU and reran the exact same model, and this is the pictures we got. And you can see that problem is totally gone away, and the percent of zeros is great, and we ended up with a more accurate model, which trained more quickly. So there's kind of these these defaults and these insights and kind of this focus where we just try to make things work well in practice. So we end up with this nice situation where, for example, there's a computer vision library where we just say import the vision library, and then there's kind of 1, 2, 3, 4 lines of code. And it gives you, so in this case, we're getting a 9% error rate after 35 seconds for recognizing which one of 37 pet breeds is an image. Basically the same 1, 2, 3, 4 lines of code will also fit this data set, which will mark every pixel in an image with what kind of object that pixel represents. And you can see where the object-oriented stuff comes in. I can say show batch, and because FastAI knows that the input type is an image and the output type is a mask, it knows that the correct way to display it is to provide a color-coded mask with an alpha overlaid on top of the image. And it's the same thing with the model. You could say show results, and it'll show you the results with the same way. So without the kind of the typed foundation, you would need a different function for every combination. It would get pretty unwieldy. So text classification, the same lines of code do text classification. And also, again, show batch is now going to show you your texts. Tabular analysis, the same basic lines of code will analyze tables of data. Collaborative filtering, the same basic lines of code will do collaborative filtering. And so this stuff turns out to work super well. So people sometimes jump on our forum, and so this person said, I just started, and I'm just comparing it to my TensorFlow 2 models, and I can't understand why everything's so much better. I'm trying to make it as less good as I can, and it's still much better. So like when you kind of build in the best practices into the library, so then somebody replied to that, founder of some company said, yep, we were using TensorFlow before, spent months tweaking, FastAI, 2 days, we're getting better results. It's important to support kind of incrementally moving across. So FastAI lives on top of PyTorch. It absolutely wouldn't be possible without PyTorch, which is just a fantastic piece of software. And so one of the things we do is, you can take the official PyTorch repository example code, delete the 30 lines in the training loop and replace it with these 3 lines, and you get all of the benefits of FastAI training with, existing code. You don't get all the benefits of the library, so things like show batch won't work because PyTorch native doesn't have the same concept of like typed tensors and things, but gets you some of the way there. So as I mentioned, and this is the thing I'm most interested in, excited about, I think, for FastAI 2 is this mid-layer API, because this is something that it's not at all uncommon in software engineering, but it hasn't existed before in the deep learning world. And it's basically a refactoring of the pieces that make up those applications. So Sylvain, who's the person who I wrote this with, created this bit about one of the pieces of this mid layer, which is the training loop. This is what a training loop looks like in PyTorch. You basically loop through epochs, you loop through mini batches, you get your predictions, you call your loss function, you do the backward pass to get the gradients, and you step your optimizer. So you basically do these things. Right? Now the problem is that there's lots of tweaks. You keep track of metrics, you have hyperparameter schedulers, there's all kinds of regularization techniques. You might want to handle half-precision floating point training. You might want to do complex training like generative adversarial networks, blah, blah, blah. So either you do what everybody else does, which is to write a new training loop from scratch every time, or you try and do what I tried to do in FastAI 0.7, which is to create one training loop that has everything, and that led to my early insanity. Or you do what we do now, which is to add what we call two-way callbacks at every point during training. A two-way callback is something where a callback can read everything, every bit of state, every bit of data, every gradient, every hyperparameter, and can write them all back, and can change the control flow. So you can, inject functionality that has access to the world and can change the world. So basically you start with a loop that looks like that, and you end up with one with the same steps, but a whole bunch of callbacks. And so callbacks end up being these like tiny little pieces of code that do a whole lot of stuff. So for example, an early stopping callback would define an after epoch, which would check for some function of the recorded values. And if it wants to stop, we use exceptions for control flow. You can raise a cancel fit exception. There's also cancel batch, cancel validation, and so forth. Or gradient clipping. So if you want to avoid activations which are going off to infinity, there can be an after backward step which actually modifies the parameters of the model and changes their gradients, for instance. So it's been amazingly successful. Basically everything we've tried to add, every paper we've implemented, every experiment we've done, we've been able to do without changing the training loop, just by changing callbacks. Yeah.
Can any other people use those callbacks other than to, like, you know, look at the equivalent of Stack Overflow and kind of black magic guess? In other words, can you reason about these callbacks if you didn't write them?
Yeah, so can you reason about the callbacks if you didn't write them? Yes, absolutely. The nice thing is that, well, for one thing, there's great documentation. And the callbacks are, they're very easy to reason about because they have very consistent names, you know, so before batch or after batch or before loss or after loss. And the other thing is we try to write our code in a way that is just super easy to understand what's going on. So one of the things that's interesting is all of the entire library is written in Jupyter Notebooks. And so we've built this new system called NVDev, which allows you to kind of do true literate programming. So if you look at the code in the notebooks, it takes you through every step of like, what are we doing? And here's a link to the paper, and here's a picture of it, and here's a graph, and so forth. And then it exports it into standard Python modules, which you can then look through in your editor. And if you prefer, you can edit them in an editor and then synchronize them back to the notebooks. So if you want to know what's going on in the training loop, then ideally you just use the documentation. But if you want to really know what's going on, you can actually say, okay, here is the piece that does one batch, right? And we really try to lay things out so you can see what's going on. So you can see here, like, no auto code formatting for us, right? Like, lay it out in a grid. Here is the list of each callback that happens in one batch. Here is a list of each piece of code that happens in one batch. Look across. Here is the connection between each bit of code and each callback, right? So, we try to make it so that you can see what's going on as well, and then you can jump into the notebook and see the experiments and the tests and so forth. So, yeah, we try to make it so that it's everybody can contribute and do their own stuff. And, of course, we have this great community as well, where we help and they help each other, which works great too. So, for example, here's a really, really important regularizer called Mixup. Mixup is a fantastic data augmentation procedure which takes two images or whatever and basically takes a weighted average of the two images and then takes a weighted average of the two sets of labels, and that becomes the data for a model. It turns out that with Mixup you can use far less data and get far better results. And so here's the size of Mixup, a GPU-accelerated version of Mixup, I might add, as a fastai callback. And here's the version from the research paper, right? So a few things to note here. The first is, the fastai callback is much shorter. And shorter is not just good because it's short, but it's good because each line of code maps pretty directly to a line in the paper of the algorithm. There's not the boilerplate. More importantly, the research code only works with one data set, SciFar 10. It only works with one metric. It doesn't work with any other regularizer, with any other training tweak, and so forth, right? With callbacks, you get the nice software engineering principle of like decoupled pieces that can work together. Another example of this, of refactoring, is optimizers. There's been a lot of developments in optimizers in the last 12 to 18 months, including people kind of combining optimizers together in interesting ways. Now, before fastai came along, these different optimizers lived in their own worlds. There wasn't really this ability to combine them. So, for example, there was a really important paper called Decoupled Weight Decay, which developed something called Atom W, which showed that the way people had been doing probably just about the most popular optimizer called Atom was all wrong. There was, a pretty minor tweak to the equation, it turned out, that made it work much better and was like much more mathematically sound. In PyTorch, it took a couple of years for Atom W to get implemented, and this is the basic code. And they basically rewrote all of Atom, plus the one tweak. fastai implemented Atom W like the day after we noticed the paper. And in our case, we had to add these 4 lines of code and this section in gray, because we had refactored optimizers. So we looked at lots of optimizers and just factored out the common pieces of code and ideas. And so it turns out that there's 2 main ideas in an optimizer. One is keep track of stuff. So the moving average gradients, or the moving average gradient squared, or the most recent gradients, or whatever. And then update things in some way. So, for example, add the learning rates times the gradients to the weights. That's the most basic SGD update step. So we basically provide optimizer callbacks to let you do those 2 things yourself and to mix and match the existing ones. And that's why our students are able to write things like this, where they say, oh, we've taken these things from this paper and these things from this paper, and it turns out we end up with something that's better than any paper. So it's really cool for kind of identifying interesting research directions and trying things out. So like this paper on reducing BERT pre-training time came up with a really nifty optimizer called the LAM optimizer. This is our implementation of the LAM optimizer that we had wrote the day after the paper came out. And one of the nice things is that you can compare it directly to the math, and it's pretty much line for line the same, except the math actually hides some things that aren't in the paper. So it actually also makes it more explicit as to what's going on. As everybody knows, one of the hard parts about any kind of machine learning is getting the data in order. And so I used to drive myself a bit crazy with this, because I would try to make it easy to get your data in order. And so so Sylvain and I had in fastai 1 dozens of classes for what if your input is images and your output is a single label classification? What if it's an input and a multi-label classification? What if it's a black and white input and a single label classification? What if you're doing the validation set is defined based on what folder it's in versus you want to do a random split? And we just ended up with all this code and all this complexity, and it was too hard for us, and it was too hard for our users. And so we kind of stepped back and we thought, oh, let's refactor all those classes. So we realized there was basically a small number of things that you need to tell the algorithm how to do it. And so basically you have to say, what are the types of my inputs? What are the types of my outputs? And one of the nice things is when you refactor it this way, you can do more interesting things like Siamese networks, where there are actually 2 input images and a Boolean output, for instance. So you don't have to always have 1 and 1. Or unpaired image translation, like cyclegans, where there's like 2 inputs and no output. And again, this is where the types come in. So we have proper types, so we can define what the types are. And then you say, okay, how do you take, for example, a list of file names and convert them into those types? And so there are certain defaults, like if the type is an image and it's a file name, by default it assumes it would image.open, that file name, but you can override those things in any way you like. Particularly important for labeling. There's 1,000 different ways to label things, and so you can, there are regex labelers, or there are the parent folder name could be a labeler. So we've kind of extracted out all the common labelers and also provided some building blocks for doing your own. And then, okay, how do you create your validation set? Is it random? Is it the last 1,000 records? Is it based on the grandparent folder name? Again, we've given some kind of classes that do some of the standard things and let you build your own. And then once you've got all these things, you then collate the data into mini batches, and there are some certain choices you make, like batch size and stuff like that. So we end up with this thing called data block, where you say, these are my types. This is the function that finds in this case, the file names. This is the class which splits, in this case, based on the grandparent folder name. This is my labeling function, which is going to do the parent folder name. And so this will do the MNIST data set. This, same basic idea with very few changes. We'll do, here's a regex labeler for doing pets. Here's one for doing multi-label classification. So we've got an image and a multi-category dependent variable. We've already seen segmentation, so an image input and a mask output. Key points, so now a tensor point is the output. Object detection, so bounding box is the output, and so forth. So, that's the bit which I'm kind of most excited about, because it means that researchers, can, or people trying to get more performance or customize things for their organization or whatever, can get underneath the surface. They don't have to write stuff from scratch, but they also have a lot of flexibility. So then finally, that is built on these kind of foundation layer. We've already mentioned object-oriented tensors. So you can go image.flip, and it flips it regardless of whether it's a pillow image or a tensor image, or even it could be a bounding box, or it could be a point cloud. All of these things have a concept of a flip. We try to really take advantage of the fact that Python is a dynamic language. There's a lot of downsides to Python, but Python is kind of what we're stuck with for now. That's where the world of deep learning is. So if we're stuck with that, we may as well make the most of it. So a dynamic language like Python lets you define decorators which add functionality to existing classes, for example. So we've created this patch decorator which will add flip left, right to each of these types. So people have not really used types, even though there are type annotations in Python, people haven't really used them that much on the whole, so we use them a lot. Newish, yeah. And they're mainly designed for static analysis, but actually, as you can see here, the basic mechanics are all there that we can use them at runtime in this way. And the patch decorator itself is like 2 lines of code. So yeah, with that we can kind of have show batch do different things, and actually, and also this is kind of nice, like show results. So for example, show results can do things like automatically color code things where the classification is wrong, for instance. So one of the things we did to make stuff like this work is we created a new type dispatch system. And again, Python is this wonderfully dynamic language. It's got a super great meta class system, which is really underutilized. And so we use the meta class system to create a new type dispatch system, which allows us to annotate like so, and end up with something that kind of feels more like Julia than traditional Python. And this is working great for us because it's actually allowed us to do things like this dispatch system does the kinds of things that machine learning people need. So for example, we tend to have mini batches with an independent variable and a dependent variable. And in PyTorch, these are represented as tuples. This type dispatch system, when it gets a tuple, by default, it doesn't look for a tuple type annotation. It pulls the tuple apart and looks at each component of that tuple that's type and puts each one part of that tuple out to separate functions based on the type dispatch system and then pulls them back together again. So that means people can create pipelines, which we'll see in a moment, where those pipelines basically say, for example, flip. And if that's a mini batch containing a point cloud dependent variable and a color image independent variable, both of those will be flipped automatically by the type dispatch system. So it makes a lot of the code just much simpler, much shorter. And so this ends up in this transform pipeline system. The idea of pipelines in machine learning data processing goes back a long time. A pipeline is just it's just function composition, basically. But one of the things that we wanted to do with pipelines, so pipelines, function composition is very important for data processing because generally to get from like a file name to a normalized image batch of tensors in the right axis order, there's just steps you take, and each one's just a function applied to the previous result. The thing is that we wanted to be able to go the other way as well, which is to start with, so you call a prediction on a model, you get back some tensor, which represents basically the end point of that processing. I need to go reverse back through the pipeline to get back, the image in a form I can see it, or the class as a string with the correct name. So these pipelines, these transforms, actually are reversible. It's not automatic. There's no concept of an inverse function in Python. You just write the inverse function each time you want to create an invertible function, and then the pipeline will automatically do the composition in reverse order. Great. So I think 5:30 is out of time, or do I? Okay, great.
You have questions. So
oh yes, I mean any time also. So sure, I'm nearly out of slides anyway. But so here's a really great example for us, especially for me, right? I tried to create a data loader with Sylvain a couple of years ago for fastai v1 for language modeling. Language modeling is a really important technique in modern NLP, and it's kind of the basis of our ULM fit algorithm I described. Simple idea, predict the next word in a sequence of words. And it turns out that if you can predict the next word in a sequence of words, that kind of model learns a lot about not just language, but about the world. So, for example, if the sentence is, some quote, as said by the 45th President of the United States, President blah, to finish that, you need to not only know about English, but about the concept of a president and which country it probably was and who was the president, the 45th president. So language models are super important. And creating a data set which kind of has a corpus of text and then the same corpus of text offset by one is surprisingly fiddly, because you actually have to kind of batch that up and feed it to a GPU a batch at a time in a way that all the batches line up with each other, and it doesn't get to cheat by kind of seeing what the next token was and blah, blah, blah. So in fastai version 1, we just had page after page of code which we just couldn't understand or maintain, even though we wrote it, you know how it is. And then for version 2, we were able to throw it all away and just use this pipeline approach, these transformations, and also, again, callbacks. So our data loader is almost entirely API compatible with the PyTorch data loader, but it has, I think, 16 callback points you can hook into, whereas the PyTorch one has, a small handful. And so it just made this code so much simpler, easier to read, easier to write, which was great. None of this is really much use unless it's fast. There's no point giving people stuff that's pretty and concise if it isn't performant enough to be useful. So we wrote, as optimized a foundation for everything as we could. So some, really easy to use parallelization constructs in Python, and then use those in, for example, tokenization. So tokenizing has traditionally been this really slow thing. We can't particularly make it faster, but we can make it so that it will automatically parallelize tokenization, and you can pick any tokenizer you want. So to do this, we tend to take a lot of advantage of the lazy generator functionality in Python, which makes a lot of this stuff kind of trivially easy. Unfortunately, Python has a global interpreter lock, which can get in the way, but most of the things that we're calling are written in C, so the GIL doesn't impact things as much as you might expect. We've written a new computer vision library, which actually runs on the GPU using PyTorch. And it's really interesting. There's a really small number of basic foundational pieces that you need in a tensor library to be able to do pretty much anything you want in computer vision. So we have this affine coordinate transform, which basically takes something called a flow field, which is basically says whereabouts should each pixel be moved to. With a flow field, you can zoom, you can warp, you can rotate. We use lazy operations so that all of the coordinate operations and affine transforms operate on the flow field. And then there's this really cool thing in PyTorch called grid sample, which takes a flow field and an image and moves the pixels and does the interpolation and padding and so forth. So that's been super fun to kind of create this thing entirely in Python where people can write new GPU accelerated computer vision stuff entirely in Python and see exactly what's going on. Yeah, so I think that's everything. And questions?
I have a couple of questions.
Please.
One, do you target a particular GPU?
Yeah, so I should mention, like, we almost entirely only write Python. Sylvain's written a little bit of CUDA C++ stuff for one particular thing we needed, but it's basically all Python. As it stands, to get decent performance reasonably reliably without too much fuss, you pretty much have to use NVIDIA GPUs. So as I say, we sit on top of PyTorch. We desperately hope that other GPU manufacturers will start delivering decent libraries so that will change, but it's happening very slowly.
Other questions?
Yep.
Behind me or me?
You?
So I have two questions. They're wrapped up together. What prompted you to create version 2? And what do you think will prompt you to create version 3?
Okay, so what prompted us to create version 2? What would prompt us to create version 3 is actually a really good question. Version 2 is a rewrite from scratch, and it was clearly needed because until version 2, we've always operated under significant time constraints. So, self-created time constraints, which is generally like, we want to have something ready for a course. So we never actually shipped a library I would say we were proud of. I would say we thought it was better than anybody else's library doing similar stuff, but it was nowhere near as good as we thought it should be. So we made a conscious decision to take 18 months off and have no deadlines and start from scratch and build the best of everything we could. So that's why we have a new type, a new type dispatch system and a new transformation pipeline and all this stuff and a new computer vision library. Because every time we got to a point where we thought like, oh, this is not as good as it could be, whether we had written it or somebody else, we decided to fix it. So it's kind of like a pretty key moment for us because we now do feel like this is the best we can create, not just in the time, but just the best we can create today, full stop. And so we've decided to also step back and like write a book about it. We're trying to write the best book we can, and to create now the best course we can. So, like, what would lead to version 3 is a great question. My hope is that version 3 will be where we really want to get to, which is like something that requires little or no code. Version 3 maybe won't be a library, maybe it'll be a GUI application or GUI application with a thin library underneath or something. Because hopefully we've built, this foundation feels like it's kind of should be solid enough that we don't need to pull it apart and start again. You know, there's so many injection points or callbacks or whatever. It feels like it should be extensible. It doesn't feel particularly tied to how deep learning is done today, but kind of fundamentally to how kind of data processing pipelines and modeling has to work. Yep.
How is your generalized ReLU different from adjusting the bias on the next the neuron is feeding?
Sure. How is generalized ReLU different to changing the bias? So the key reason is batch norm. So batch norm will move it to where it wants to, and so then the ReLU will kick in, and then the output of that will have the an average you don't want. So you still end up with a non-zero mean at the end of each kind of super layer, if you like. So we saw that in practice, having a non-zero mean makes it very hard to maintain a unit variance. And that's actually the thing you really care about. And I will say, it turns out this observation, we were not the only ones to make it. This idea of centralized ReLUs has appeared elsewhere. There's a thing called CELU, C-E-L-U, which is a centralized exponential unit. And yeah, how much it matters depends a lot. Like if you can have batch norm everywhere, it's much less of an issue, but particularly for something like a RNN, where batch norm's not really an option. Or things where you have to have very, very small batches. So batch norm doesn't really work. This kind of really good initialization matters, and it's very hard. It's not really possible to get really good initialization without a centralized activation function. And some of our students have actually found now, I don't think any of it's published yet, but there are combinations of specific inits and centralized activation functions that lets one of our students train 1,000-layer deep networks without batch norm, which is pretty cool.
Anybody else?
Yeah, you talk about this group of students, and you talk about a lot of code, or at least maybe not in terms of lines, but in terms of semantic density. I wonder, this larger community, how much are you getting feedback at the code level and also at the peer-reviewed publication level? Even if it's like an IAAI kind of paper, how often does this happen? How big is that community that's sort of heavy hitter contributions is what I mean to try to separate?
So we have a peer-reviewed paper in Information, which, honestly, I mean, the reviewers were super helpful, but the help was around wording tweaks, little missing citations. There was nothing surprising because of the wider community who's already been pounding on this for a while. So we do all of our work entirely in the open. And every time we push something significant, we tell people about it on the forum.
You misunderstood my question. Maybe the answer is 0. What I meant is not you.
No, I know. I'm getting there.
I meant the big, yeah.
Yeah. So as a result of that, there is a hardcore group that keep up, and I try to help them keep up. So, for example, when FastAI 2 first kind of got to a point where it could do things, I did, I think it was 12 hours of video code walkthroughs with a group of people online with me asking me questions. And what we found is a lot of people are really interested in AI, and a lot of people are interested enough that they give up their jobs and spend a year studying it. And a lot of those people turn out to be like super high achieving kinds of people. A lot of people who can do that because they just sold their company or whatever. So we kind of have this really nice hardcore community of people who are, absolutely trying out every new line of code as we add it, telling us about things that don't work, building new things. So there's and then they form, on the community, they form these kind of nice study groups. So there's an audio study group. So there's no fastai.audio yet, but there is a fastai.audio library built by this community of people who know a lot more about audio than I do. Same with time series. There's a nice time series study group who have been creating state-of-the-art results with fastai, with time series, building time series applications. It's not, it's a minority of the community, which, as it should be. Most of the community are just using it to do stuff. I will say this, though. PyTorch is by far the most popular library used for research. So like at just within the last 12 months, at NeurIPS, it went from TensorFlow being like 75% of the publications to PyTorch being like 75% of the publications. And increasingly, as fastai2 matures, more and more of those researchers are looking to do stuff with fastai as well, and then naturally have a tendency to push deep into the code because they need to try things that haven't been tried before.
But order of magnitude, 10, 100,000?
How many people?
Yeah, of kind of this hard-ish core group.
It would be hundreds,
Wow.
But I also know there's a lot more than I know about. Like sometimes things pop up. So like a couple of weeks ago, this paper appeared from D.E. Shaw Research. So D.E. Shaw, David Shaw, was one of the top, billionaire hedge fund guys who founded a research group a few years ago. Cool. Okay. So he's now spending his time doing biotech research, and I was delighted to find this paper appear where they're using fastai to create a state-of-the-art protein analysis system. And I only found out about it because one of those people came back to take our most recent course and introduce themselves in the forum and said, "Oh, by the way, you should check out our new paper." So I know there's a bigger group. Another example, I know somebody from, the VP of AI and ML at GlaxoSmithKline contacted me last week and said, "Hey, everybody who comes to GSK takes your course. Your library is integrated into our HPC clusters." And I was like, I had no idea. So it's very hard to judge.
We've run out of time. Thank you very much. And
thank you.